Hello everyone, Aaron here. Welcome back to Leetcode. Today we are tackling the validate binary search tree problem. That's problem number 98. I'll be honest, I'm hoping this is a bit of an easy one because I've managed to hurt my arm, so I am working with one hand today. That will slow me down a little bit, but hopefully the brain is still working and not too distracted by the soreness. Right, the problem is stated as follows. Given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So, for example, this top one is fine, 1 is less than 2, and 3 is greater than 2. This one is not, because although 1 is less than 5, 4 is not greater than 5, and also 3 is not greater than 5. So the way we're going to do this is with two recursive functions, basically. We're going to do def left valid with max tree if we need a self in there. Oh man, this is gonna be slow. If tree is none, return none. Otherwise, what we want to do is, so the reason I'm asking for the max here is because the largest value on the left side must be smaller than this. So I want to do, no, actually, rather than doing this, let's do left valid with max, let's do valid with bounds. So this is going to be true. I'm going to move to trying to use two hands. That's how this works. True, none, none. Then on the, we want left valid, I don't care, left max. Oh, no, I do care. I want left min. Left max is self dot valid with bounds of tree left right valid right min right max self valid with bounds. Sorry, just need a sec. While I'm recovering. So the idea here is that I want to find the min and max on each side, because here I need to make sure the max is less than the value, and on this side I need to make sure the min is the value. And when I return up the tree, I also want to report the absolute min and the absolute max, so that depending on whether this was the left or right, we can accurately decide, well, whether this is correct under its parent, and so on and so forth up the tree. So actually in here, if not left valid, return false. false, none, sorry. None. Valid with bounds. Tree dot right. If not right valid. So the reason I'm happy to skip trying to calculate the bounds if the subtree isn't valid is because as soon as any subtree is invalid, I can just invalidate the whole tree. It's not going to magically fix itself as we recurse back up. It's only in the case where it's true that we need to consider the bounds, and even that's not entirely true here. If it was an empty tree and it returned true, then the bounds will be none. We just need to check that at the next layer. So if we've got here the subtrees are valid, and then basically if two hands again, this is just painfully slow and it's going to get painfully sore, so we'll keep swapping between the two modes. If left max and left if left max is none, then it's fine. Or left max is less than tree.val. And right min is none, or right min is great. Actually, do you know anything about the uniqueness of these? It says less than or greater than. I guess that means every value is unique. It's a wee bit unclear. Right min is greater than tree val. So if the left is valid and the right is valid, we want to return true left min right max. If left min is not none, else tree.val. Right max if right max is not none, else tree.val. So the reasoning behind this logic is if the left min was none, no, and else false none. If the left max is none or left max is less than true value, so down here this doesn't exist, so this is fine, or 1 is less than 2, that's also fine. Right min, well, this thing doesn't exist, so this is fine, or 3 is greater than 2, so this is fine. Then we want to give back the truth, say it is valid, but also that we want to give back the left min if it exists. In this case it would be a 1, so it does exist, and same with the right max, it's 3, so it does exist. But if it doesn't exist, so down here, for example, it does not exist, so we want to just say 1. 1 is the minimum thing. Basically, this is the degenerate case. So then to kick it off, self.valid with bounds root. And I only care about the actual truthiness, not the whole tuple that I've constructed here. Oh, right. Ow. Let's see if this works. Have I made any dumb mistakes? I have made dumb mistakes. I need a backslash there. That seems to work. Let's use the other test case as well. This one should return false. It did indeed correctly return false. Okay, let's submit it, see what happens. Excellent. And 68 milliseconds faster than 55.51. Oh, that's surprisingly quick. So, this is quite a cute little problem. It requires a bit of understanding about what a binary search tree is all about. Hopefully this was entertaining for you. Sorry about my typing and concentration is a little off today, but hopefully next time I will be back in full performance. Thank you very much for watching. Remember to like, comment, subscribe, all of that good stuff, and I will see you next time. Bye.